Hi, my name is Christoph Nusslein, and I'm part of Group 36, which includes myself, Amro Al-Sharif, Carlos Carrasquillo, Sam Deal, and Ethan Schoenhout. And today I'm going to be talking about leveraging ML for hurricane tracking and path prediction. So a bit of background on hurricanes in general, specifically the ones we're going to be looking at in the Atlantic region, is that large storms can develop in this region over the course of the late summer and early fall, and these large tropical ocean waters can cause strong convective currents, creating powerful cyclone systems. These resulting hurricanes can be highly destructive, so predicting their behavior is important for saving people's lives. Now, there is a huge wealth of existing weather data that the National Oceanic and Atmospheric Administration, or NOAA, has tracked since 1851. Which they have released as the database HERDAT2, which provides weather information for each storm on record at 6-hour intervals. Our goal is to leverage this database to create complex predictive models that can provide insight into future storms as they develop, which can greatly help in reducing damage, acting as early warning systems, and so on for people that live in coastal zones that might be under threat of this sort of event. Now, the relevant features of HERDAT2 include not only the storms and their appropriate identifications, but also the date, time, status, and progressive location with respect to time of each of these storms, as well as some relevant weather information, including maximum wind, minimum pressure, and so on. There are also associated events, such as whether a storm makes landfall or not, that we will come back to later. Now, incorporating ML into this sort of task means leveraging it in two ways. So first, by clustering important storms by events, and secondly, by storm trajectory prediction. So firstly, unsupervised learning and component analysis was used here to determine the most important factors in storm development, and time-distributed sequential learning models were used to predict the future paths of hurricanes. Now, knowing whether a storm becomes a hurricane and whether it makes landfall is extremely important for people in danger of being affected by these extreme storms. So our clustering methods were used to identify important features in the data set. And for these, we had k-means and Gaussian mixture models, which were used to determine whether storms were present that didn't become hurricanes, storms were present that did not become hurricanes but made landfall somewhere along the coast, and storms that did become hurricanes and also made landfall. Now, the actual data that we looked at was the starting position for each storm, as well as their change in direction and maximum wind speed. We fed these through a PCA set and then ran them through our model to cluster them appropriately, and then spat out the associated 0, 1, and 2 corresponding to the labels that we set. We did this for both k-means and GMMs. Now, the resulting model comparison shows us that on a plot of all the origin points for every storm that was investigated, the ground truth and the k-means and GMMs setups are decently similar, although there is much greater distinction between the k-means and GMM models and the ground truth. However, that being said, k-means and GMMs were shown here to cluster quite similarly. To determine the number of clusters that were used, GMMs and k-means were both run through the elbow method and silhouette coefficient, with the elbow method for k-means and the silhouette coefficient for GMMs, with the goal being to investigate the optimal number of clusters, which for both was 3. Here we show the confusion matrices between ground truth and the predicted labels, which shows us that low mutual information, accuracy, and homogeneity scores resulting from these comparisons indicate that the learning currently present might not be sufficient without more advanced feature engineering. Moving on to hurricane trajectory prediction, We began by splitting HERDAT2 from a dictionary that we'd stored it in previously into an array, splitting each of those splitting each storm's time series data into features and labels, moving those features and labels into individual windows and accompanying predictions, randomizing the order, and then splitting the data set let us separate everything appropriately in a random manner into 80% training, 10% validation, and 10% testing data. Now, each of these time series features included here was position in XYZ coordinates, pressure, and maximum wind speed. And the corresponding label set was the XYZ position of the center of the storm at some point later on in that storm's future. To predict the trajectories used here, or investigated here, we selected 3 different models, the first of which is a recurrent neural network, which consists of long short-term memory layers, dropout layers, and a final fully connected layer. We also used a convolutional neural network, which consists of convolutional memory layers, dropout layers, and a final fully connected layer. And finally, a temporal convolutional neural network, which here comprised several blocks of 1D convolutional layers, as well as weight normalizing blocks and ReLU blocks, as well as linear layers at the end. Now, the model hyperparameters selected for each set were quite similar, although for RNNs, each parameter was much greater. Investigating the final performance of each model, it is shown that CNNs and TCNs show an initial sharp decrease, but then, especially with CNN, settled on some set loss before the gradients of the internal model architecture were able to move past a set of patterns and finally move on to much greater loss reductions, whereas RNNs are much more consistent overall. Now, for predicting hurricane trajectories and combining our approach with future work and models, we suggest that more rigorous hyperparameter optimization and combinations of different features and potentially even generating new features from existing ones might result in more optimal principal component combinations. And furthermore, we would also like to suggest expanding this model setup to international weather data, both for hurricanes and other storm types like typhoons and cyclones, as well as other tropical storms, so that we could thus increase our data set. Thus, we were able to show that both k-means and GMMs can be used to classify storms by event types, although we found that one of the most important aspects of accurately classifying storms by their labels instead of simply clustering them is to transform the existing data into a feature space that cleanly separates the ground truth labels. For trajectory prediction, both TCNs and RNNs show promise for predicting storm trajectories, but they're still limited. CNNs potentially even more so. Many important path-affecting atmospheric conditions of a storm are not present in this dataset, meaning that the models trained here might not be able to fully account for ground truth storm dynamics. Thank you.